Hello everyone, my name is Ricardo Antonio Mendez Mendoza, and today I'm going to talk about my poster titled Understanding Optical Intervalence Charge Transfer Processes. This is in regards to the topic of mixed valence compounds, which have more than usually bimetallic complexes, in which the donor and acceptor species are two metal cations that have more than one available oxidation state, and in consequence, the overall complex, the mixed valence species, can have more than one available oxidation state. In this species, according to Hoche theory, the intervalence charge transfer consists on the electronic transition of transfer of one electron from one side to the other, from the donor metal to the acceptor metal. This is related to the Marcus theory of charge electron transfer, but compared to Marcus theory, where the process involves thermal energy, delta G hash, this process is done through an optical um, energy by involving an optical absorption, the absorption of energy from the visible infrared or the ultraviolet region of the spectrum. The expression for this is the one shown here, which expressed in wave number terms is the one shown on the right. Where the absorption maxima consists in the sum of the free energy terms, which depends on the difference of the donor and acceptor um, potentials obtained by electrochemistry, plus the reorganizational energy term that depends on the full width at half maximum squared over 2310 wave numbers. The charge transfer process can be done through space between the proper alignment of atomic orbitals or through a ligand, in this case an oxygen atom. And it's a super exchange process where the ligand donors an electron to the metal 1 and is followed by the another electron transfer from metal 2 to the ligand, and the overall process can be considered, I'm sorry for this figure, has the electron transfer from metal 2 to metal 1. Among the results that we have are the theoretical proof that the metal to metal charge transfer consists in the sum of the transitions between metal to ligand, ligand to metal, and between ligands. We also found an analogy between the monometallic species, the bimetallic compound, and a dimer of the monometallic species, which can be seen as a bridge between both cases, between an outer sphere electron transfer on the left and an inner sphere electron transfer on the right. We analyzed this for the case of one of the most known cases is for Prussian blue, which consists in the sum of the hexacyanoferrate uh, direction, but can be seen as the sum for the hexacyanoferrate and the hexaquo um, ferrite, which can be produce the complex between the hexacyano and the hexaquo ferrous species. We also showed that the dimer species, its transition maxima and its reorganizational energies can be obtained by the precursors, the monometallic precursors, and we also developed a theoretical equation for the analogous to Nernst equation, where the potential energy difference between the optical transition can be seen as the sum of the is equal to the potential uh, difference between the donor and acceptor. I'm sorry, the optical way is equal to the electrochemically obtained one plus a C term, in this case related to the reaction equilibrium between reactants and donors, designated as Q. We apply this for two cases. The first one, complex between hexacyanoferrate and cis and trans complexes of cobalt by the substitution of the chloride ion. The monometallic precursors are above, the bimetallic precursors are below, and we show the cyclic voltammetry of one of the cis bimetallic compound with the absorption spectrums of the cis and trans species. And in this case, we see based on the potentials that the difference of electrochemical potentials for between the donor, which is the hexacyanoferrate species, are at around 0.24 volts, and the acceptor, in this case the cobalt complex, at minus 29 volts, is approximately 0.54 volts. In the case for the cis complex, using the trans complex, it will be a little higher. But comparing for the outer sphere, in this case, the outer sphere dimmer, we could consider it. The difference increases to 1.09 volts, compared, whereas the trans dimmer is the complex. I'm sorry, is at 1.22 volts. In both cases, the potential difference is greater than that of the precursors. Sorry. What is interesting is that in this case, the donor, in this case the hexacyanoferrate, conserves its status as donor, considering that its oxidation potential is the one to the right, whereas the acceptor preserves its position as the acceptor, the cobalt complexes. And using the outer sphere equation, we found that the highlight in green on below, we find that the cobalt to cobalt outer sphere transition for the complex, for the monometallic complex, for the cis and trans cases, resemble a lot that of the aqueous cobalt +2+3 intervalence charge transfer. The second case was interesting compared to the first one for using Prussian blue. In this case, the hexacyanoferrate complex reacts with iron chloride. It could be +2+3. In this case, the potential difference suggests from the precursors that the donor is the iron chloride at 0.7 volts, whereas the acceptor will be the hexacyanoferrate at 0.33 volts, reversible wave for each. Whereas in the bimetallic, in the complex that makes an array, the donor and the acceptor roles reverse. The iron with the with the carbon attached to it becomes the donor species, whereas the iron that is coordinated to the nitrogen, the one from the iron chloride, becomes the acceptor. We have the cyclic voltammograms of the Prussian blue and its absorption spectra deconstructed in Gaussian shapes. I'm sorry. And in this case, we have the same relationship that the monometallic precursors resemble, are related to the bimetallic cases. One, the outer sphere, the dimmer, and the other one, an inner sphere, the bimetallic complex as such. We find that the metal-to-metal charge transfers are somewhat similar between the outer sphere and the inner sphere, and the difference comes precisely because of the formation of the complex, but also from the size of the Okay, from the coordination change in the coordination sphere between what will be the dimer, the bimetallic complex, but one keeping the water molecules, and the other one that doesn't keep the water molecules, which is an interesting observation or result because the it will indicate that if we have a big change in the coordination sphere, it implies a reversal or inversion, more likely, between the donor and the acceptor species. Another analysis we did will be for the charge transfer for the ligand to metal 1 pair. Considering that in the deductions we found is that the ligand to metal charge transfer follows the same expression that the metal to metal charge transfer or intervalence charge transfer. Thanks to which we have the difference of electrochemical potentials and the experimental value, and we obtain a different value for the denominator in the Hodge equation, value higher. We also found a ligand-to-ligand charge transfer according to the red equation, located at above 61,000 wave numbers in the UVC region. And using the blue equation, we find that the reaction constant of equilibrium between the products and the reactants is 0.14, namely that a small percentage of products are photogenerated compared to the reactants by the excitation of the IBC band in the non-standard conditions. This will be the main points, the main results from our study, but more analysis needs to be done in cases already reported and further work being done, especially in the case of the I'm sorry, especially in the case, for example, for the um, denominator term or for the reaction equilibrium and their values of each and their implications, not only in these systems but other cases with applications, for example, in catalysis. Thanks for watching, and I hope to see you in person very soon.